I'm Curtis, and I'm going to be talking about how we generated a collection of unsatisfiability proofs for Lamb's problem. Lamb's problem comes from a branch of mathematics known as projective geometry. And a principle of projective geometry is demonstrated right here. So this is actually an image, it's a painting, and the lines in the image are actually parallel in real life. However, when projected onto the screen, it looks as if they all meet on the right here. This is demonstrating a principle of projective geometry, namely that any pair of lines are going to meet somewhere. I'm going to come back to that, so just keep it in mind. First, I want to talk about the software systems that we used in generation of our proofs. The first of which is known as a SAT solver. SAT is just short for satisfiability. This is a classic problem from logic where you're given a logical expression and you're asked, can you make it true? Can you find a way to satisfy the expression? Interestingly, a lot of problems which have nothing to do with logic can be reduced to logic in order to solve them. An example of this is this coloring problem here. Say you have a queen on every square of a chessboard, and you want to color the queens so that queens of the same color can't attack each other. Turns out you need at least 9 colors to do this. There's no 8 coloring, but how would you show to someone that there's no 8 coloring? You could give them the 9 coloring, but that wouldn't prove there's a better coloring. And so the idea is, if you can reduce this problem into SAT and run a SAT solver on it, the SAT solver will actually generate a non-existence certificate for you. This certificate can then be given to the third party, and then they can check for themselves that yes, indeed, the 8 coloring does not exist. The other type of software system we're going to be using is known as a CAS, or computer algebra system. These are systems designed to do mathematics. An example of this is shown on the slide here. Say we have these two graphs. They look different at first, but you give them to a CAS, the CAS will actually test for isomorphism and actually produce an explicit isomorphism for you, shown at the bottom here. This brings me to the SAT plus CAS paradigm. SAT solvers are really good at doing search. The SAT problem is inherently a search problem. And CAS are really good at doing expressive mathematics, right? And there's lots of problems where you want both. You want really fast search and expressive mathematics. SAT solvers alone are not so good at mathematics, and CAS alone are not so good at doing search. This is the impetus of the research program I started a couple of years ago called MathCheck. So this is a software that we've used to run lots of different types of combinatorial searches. An example of such an object that we found is shown in this slide here. This is known as a Hadron matrix, which I don't have time to get into, but check out the website if you're interested. So it looks very pleasing to the eye. And in fact, any 2 rows in this matrix are going to be orthogonal to each other. But coming back to projective geometry, I love this problem because it goes back all the way to Euclid in 300 BC. So Euclid did something interesting. He defined the axioms for geometry. He had several axioms, and they were all very simple, except for this one known as the parallel postulate. So his parallel postulate was more complicated, and so mathematicians wanted to prove the parallel postulate in terms of the simpler axioms, right? This would be a natural thing to do. However, they couldn't do it for 2,000 years, and eventually it was realized why. This is an impossible task because there are going to be cases where the parallel postulate is going to fail, such as in our projective geometry. As I mentioned, in such a geometry, all lines are going to meet somewhere. So in fact, there's no way to prove the parallel postulate because there'll be cases where it'll be false. The simplest example of this is in these finite cases here. So these are what are known as finite projective planes. They satisfy the projective axiom and Euclid's other axioms, but they have a finite number of points, which is why Euclid wasn't considering them. Now, they also satisfy an order condition, saying that the same number of points line, every line is going to be 1 greater than the order. So the question then is, for what orders do projective planes exist? It turns out mathematicians have studied this problem extensively, and they exist in all orders up to 9, well, with the exception of 6. At 6, there's a theoretical obstruction which eliminates this case. So you can just rule it out. At 10, this is a very interesting question because no such projective plane of order 10 is known, but also no theoretical obstruction to a projective plane of order 10 existing is known. So really, it could go either way. And indeed, Clement Lamb studied this problem extensively in the 1980s. Hence, the problem was named after him. And in fact, with his team of researchers, he actually solved the problem using a massive supercomputer search. So was this a correct solution? It's not a proof in the mathematical sense of the word because it used custom-written software. Moreover, the software was run a single time on a single piece of hardware and no certificates were produced. So at the end of the day, when the computer outputs search complete, how do you know? You just have to trust the computer. Maybe there was a glitch in the computer, maybe there was an administration error, maybe there was a bug in the program. You know, anyone who's written custom-written software knows it's almost impossible to write without making bugs. So this is a lot of trust, and this was the start of our work where we wanted to put Lamb's problem on a sounder foundation by generating non-existent certificates. So how do we do this? We're going to use a SAT solver, as I mentioned. And the idea is to use a SAT solver, you have to come up with a reduction to the SAT problem in logic. So we're going to do that and then generate a collection of non-existent certificates, which can then be verified by a third party. So to encode your problem on a computer, we're not actually going to use those nice colorful diagrams. We're going to use a 0-1 matrix known as an incidence matrix. The idea is the lines of your plane are going to be represented by rows of the matrix, and the points of the plane are going to be represented by columns of the matrix. Then you have a 1 in the ijth entry here if the ith line contains the jth point. Then you can check, here's 3 examples, that all of the axioms of projective plane are satisfied. In particular, the projective axiom saying that any 2 lines meet at a unique point becomes an inner product condition. The inner product of any 2 lines is going to be exactly 1. For example, the inner product of the first 2 lines here is exactly 1 because they meet in exactly the second column and no other columns. Now, there's a nice representation between Boolean logic and the 0-1 matrices, right? Because true values can be represented by 1s and false values can be represented by 0s. So we're just going to need to have a variable for every entry in our matrix, right? And then how do we go about encoding the projective axiom? All right, so this is an inner product condition. You know, the SAT community has a well-developed tricks of how to encode such things. You can say you want to break it up into its most simplest components, right? So if 2 lines are going to meet at exactly once, they're going to meet at most once and at least once. So let's go through each of these in turn. So first of all, let's say the lines meet at most once. So I've given you 2 random lines here, and I'm going to go over an example. So the gray entries are unknown, the white entries are 0s, and the black entries are 1. So if these lines are to meet at most once, take a look at the 2 highlighted entries. These can't both be true. If both of these were true, the lines would have an inner product of at least 2. They'd meet at least twice, and that would be a contradiction. So at least one has to be false. In Boolean logic, this is said as not A or not B, shown down at the bottom here. This is what's known as a clause. There's going to be lots of clauses which look like this. I'm just showing you one for the sake of example. In the second case, let's take the same 2 lines, but this time, let's look at these points, and we want to say that they meet at least once. Now, all of these points can't all be false. If they were all false, you can see by inspection that the lines would not meet at all. Their inner product would be 0. Therefore, you can learn another clause which forms part of the encoding again, and again, there'll be lots of clauses which look like this. This is just one example. Now, where does the cast comes into play? The cast comes into play as follows. As the SAT solver is working on the search, it's finding partial solutions. Here's a 4.6 line partial projective plane. We can give it to the cast, and the cast can then analyze, as I mentioned, it's really good at looking for isomorphic structures. And so here, what it will notice is that if I rotate this partial projective plane 180 degrees, I get something which is isomorphic. It looks the exact same. It's symmetric. So in fact, we can actually just block it, right? By the reasoning that anything which is extendable from the first is also going to be extendable from the second. So you're not actually losing anything non-equivalent by blocking just the second. And this is powerful because every single time there's another symmetry that you detect, you can block more and more of the search. So in the end, we generated a collection of non-existent certificates for Lamb's problem. It turns out that there's 3 necessary cases to solve, and we solved the second case in our IJCAI paper in around 30 hours. This is in comparison to a previous approach, which required around 16,000 hours on a similar computer. The complete set of certificates will appear next year at our IJCAI paper. So in conclusion, I just want to stress how applicable the SAT plus CAS method is to other problems. Yes, the Lamb's problem is a very nice application of SAT plus CAS, but it's far from the only one. In fact, whenever you have a mathematical problem which requires fast, verifiable, and expressive searches, the SAT plus CAS is a great way to go about structuring your search, because the SAT solver provides you with a fast and verifiable search, whereas the CAS provides you with an expressive search. Now, yes, you might have to structure your problem in a different way, right? You might have to be able to translate some constraints into SAT and translate other constraints into CAS. However, if you're able to do this, the upshot is huge because you don't have to write special purpose search code. And this is code I know, speaking from experience, is difficult to write, even harder to make efficient, and almost impossible to verify. Whereas if you use a SAT solver to perform the search, you have a SAT encoding, which is relatively easier to write. SAT solvers are already very efficient, and they already have tools that will perform certificates checking. So you don't even have to trust the SAT solver in the end. You just have to trust the verifier. So we're really excited to push this to new applications and new domains. So I'm looking for students and more collaborators to help me in this work on this. So if you're interested, get in touch. Contact info is on the slide here. And I'd be very appreciative if you pass on the word to anyone else who you think might be interested. So thank you so much, and I'll be happy to take any questions at IJCAI.